Okay, so we are now in week number 6, I believe. This is lecture number 11. And we are on chapter 10, which was on displaying quantitative data. And last time we worked on histograms. Or we started speaking about histograms. And we talked about how the columns represent the frequency, how often each one occurs. The width should be the same. If you look here in this diagram, there's a gap. You don't just skip it and move this closer. The gap is supposed to be there because we want every number on the x-axis to be in the right spot. We want the scale to be correct. And then we also spoke about what happens if you're on the boundary. You get to pick in advance whether they're going to go left or right. But in this case, borderline cases go on the right as far as this class is concerned. But just be aware out there in the world, as long as you're consistent, it doesn't really make a difference. We also talked about the fact that the same data can be represented by a different histogram if our widths change. And depending on your goal and what you're after and what you're trying to represent, you might pick one version over the other. There's no best width out there in the universe. And that takes us to the new material, which is relative frequency histogram. So the first thing you should understand or recognize is that a relative frequency histogram looks exactly the same as a histogram. If you compare this to the one that we have here, we see that they are exactly the same. The scale on the x-axis is exactly the same, 0, 10, 20, 30, 0, 10, 20, 30, saturated fat in grams, saturated fat in grams. The columns are exactly the same, the gap, the outlier. What changes is the vertical scale. A regular histogram, we count the frequency. The frequency is how many occur in each of the bars. So for example, from 2.5 to 5, there's a count of 8, which is why the top of the bar goes to 8. Seems very straightforward. But if we look at this one, the top of that first bar is no longer going to 8. It's actually going to a decimal, 0.12, 0.11. This is obviously not counting, because how can you count 0.11 objects? It doesn't make any sense. So what is this instead? This is a relative frequency histogram, where instead of telling me the exact number, you tell me the proportion or the percent that go in each category. So let's look back here. How many burgers were there in this example? Did they give it to us, or do we got to count it ourselves? Let's count it ourselves just to make sure that we're counting correct. How many are in the first bar?
There's 8 in the first bar.
8 in the first bar. How many in the second?
11.
11. How many in the third?
6.
6. The next?
9.
Next.
6.
Next.
8.
Next.
5.
Next.
4.
4. Next.
6.
6. Next.
3.
3. Then
2.
2. Then. All right. So 69 hamburgers. I seem to recall that. I think they said that somewhere. Yeah, 69 burgers. Okay, right there. Okay. Now, what percent of those 69 burgers go in the first category? How would I compute that? How do I compute the proportion that falls in each bar?
8 divided by 69.
8 divided by 69. I just did it on my calculator, and I got 0.116. Does it seem like it might be in the vicinity of 0.116? Anyone?
Yep.
Yeah.
Okay, so 0.116, it seems very reasonable. And similarly for the other ones. So In order to compute the relative frequency histogram, you have to know first the total number and all the frequencies individually. Because if you don't know the total is 69 and you don't know there's 8 in this one, you can't divide them because you don't have the numbers in the first place. So you need all the same information, but you get a different y-axis scale. Can anyone think of a reasoning why you might prefer proportions to actual counts or vice versa? Not necessarily a mathematical question, just a out there in the world question. Can you think of a situation where I might prefer the counts themselves or I might prefer the proportion?
Maybe if there's a great difference between the counts, you'd prefer the relative frequency to show off the difference. That way you don't have to make the y-axis as big.
Maybe. But remember the shapes are going to be exactly the same with the histograms. So whatever the counts are, I just have to set my scale so that it fits on my graph because they're going to look exactly the same. It's a carbon copy, right? So if it fits in one, it's going to fit in the other, right? Yes, no, maybe so.
Sorry, I thought that I was unmuted. That makes sense.
Okay, so for me, if I tell you that there's 8,000 things in one category, you might say, oh, 8,000, that's a lot, wow. But if there's gazillion, or 8,000 out of a million, then 8,000 by itself doesn't really give me a lot of information. It's the proportion that really is the more informative value. Or if I say, oh, I counted 7, not 8, you might say, oh, those are kind of close to each other. 7 and 8 are kind of close. But if there's only 10 in total, 7 and 8, we're talking about a 10% difference. So there could be reasons why one might be better than the other, and that's not mathematical. That's more, just common sense and intuition and whatever the experiment is. So in this case, when it says what proportion of the burgers had fewer than 10 grams of saturated fat, how would I compute the proportion that had fewer than 10 grams of saturated fat? How would I compute that?
Would you add all the
Add all the what?
saturated fats before 10?
Would I add these numbers, you mean?
Yeah.
Well, I could do that, but the problem with this is that I don't have these numbers. I can guess, I can come up with nice approximations, but if I want to be more exact, what should I do? If I want to be more exact than what my relative frequency can provide, what should I do?
Could you use the first histogram instead, where it gave you like the exact numbers?
Yeah, that's what I would do. I would go back to here and say 8, 11, and 6. That's a total of what, 25? So I would do 25 divided by 69, which would give me 36.2%. And if I added these numbers, I'd get approximately the same, but doubtful I'd be as accurate. Does that make sense? Yes, no?
Yes.
Okay. So when examining graphical displays of quantitative data, so look for the answers to the following questions. Okay, so here's an example. The histogram gives the age at which 315 dogs were diagnosed with diabetes. So first, what is the source to the data? Where's the data coming from? Where's the information coming from?
Somewhere in southern Brazil.
Yeah, okay. There's some, well, whoever did the study picked dogs in southern Brazil, and the name of the article or the name of the magazine that it published in is certainly not English, but it doesn't look Spanish. Anyone here speak?
With Portuguese.
What is that?
With Portuguese.
Oh, it is Portuguese. Oh, okay, Portuguese. So, yeah, so probably Portugal, or where do they speak? Where do they speak Portuguese in South America? Do they speak Portuguese in Brazil?
Yeah.
Oh, okay, so probably in Brazil. Okay, there we go. Now, why do you care about the source of the data? Well, different sources are more reputable than others. So always, is it coming from TMZ or is it coming from, the Wall Street Journal or something like that? You might trust or believe in some data versus others. Next, what are the variables and what are the cases? That is, what was measured and who or what was it measured on? So in our example, what exactly was being measured in our example here?
At what age dogs get diagnosed with diabetes?
Yep. Okay, very straightforward. They tell it to you at what age dogs get diagnosed with diabetes and who or what was it measured on? What are the cases in this example?
315 dogs.
These specific 315 dogs. Not just 315 dogs, but these 315 dogs. These are the ones that were diagnosed, that were studied. Does the distribution have any unusual characteristics such as clusters, gaps, or outliers? Do we see anything really unusual here? As there are lots together and then a gap? Is there one or two in the middle of nowhere? That doesn't look like it. I mean, certainly the majority of them got diabetes at roughly the same age or in a few years apart. And there were some who got it very young and some who got it very old, but it doesn't look like, I mean, obviously it's unusual to get diabetes young or old, I guess, because not many got diabetes at an old age or young age, but nothing out of the ordinary that we would expect this data to be
Not true.
controversial.
Not true.
Yeah, exactly. Okay. Then I think we've talked about this before, the shape of the distribution. Is it skewed to the right where there's a long tail on the right side? Is it skewed to the left where there's a long tail on the left side? Is it symmetric where it looks the same on both sides? Normal is like a bell curve. So symmetric, normal, symmetric, not normal. In our example, which would this be, if anything? Again, it doesn't gotta be perfect, just ballpark.
Symmetric and normal.
It looks pretty symmetric and normal here, right? It looks fairly symmetric and normal. So we like symmetric normal graphs. Those are the most well-behaved and from a mathematical standpoint, just the best graphs that are out there. Where is the distribution centered? If you had to give it a center, where would that be in this example, roughly? Where would the center of this data be if you had to give it a value?
10 or 11.
Yeah, around here. Yeah, 10 or 11 looks good. So, how do I turn this? Sorry. There we go. All right, 10 or 11. Next, what can you say about the variability in the values? Do the values vary significantly? Is there a lot of variance?
Yeah, because it's almost 0% at age 2, but it's 16% at age 10.
Well, I don't mean variance in terms of the values. I mean variance in terms of the range of possible values. Like, like 0 to 1,000,000 would be a pretty big range in comparison.
No.
So it's not how much of each value that we care about when we talk about the variance, but the actual values themselves.
So in this case, that would be the age, right?
In that case, that would be the age, right? That's the x value. So it's like from 1 to 17, right? Right? It goes from 1 all the way up to 17. That's what the study says. But
Then I don't
go ahead, I'm
think
sorry.
I don't think there's a big variance then.
There's not a huge variance. And in fact, most of the data is pretty centrally located. right? Most of the data is all near the center with very little on the edges in the grand scheme of things. So actually the variance would be pretty small in this example, I would think, if we were to actually compute it. And then what are possible interpretations or explanations of any patterns in the distribution? So when I look at this, is there anything here that I might have to say, wow, why is this the case? Well, could be because of this or because of that. Is there anything here that just stands out that kind of requires an explanation for why that should be the case?
They're really old dogs not getting diabetes, maybe.
So why would you think that very few old dogs don't get diabetes?
I would say maybe because most of them don't live to that age.
That's a wonderful example, right? I mean, if the majority of dogs get diabetes around 9 or 10, 11, very few of them would live to this age without getting it. What about these ones here on the other ends? I mean, 1-year-olds, 2-year-olds, 3-year-olds getting diabetes. Does that require explanation?
No.
No, so it's normal. Anyone here know a lot about dogs?
Well, they're still young, right?
They're extremely young.
Yeah.
They're extremely young. So is diabetes, I mean, in humans, you can get different types of diabetes, right? You could have, I think, I'm not a doctor, this is certainly not my area of expertise, but from what I know, there's like type 1, there's type 2, there's different types of diabetes, correct?
Correct.
Yeah.
And some of them are genetic, and other ones you can get on your own by your lifestyle, right?
Yeah, the lifestyle one is also kind of genetically predisposed, but
Okay.
it is more lifestyle.
Okay, so it could be that, you know, these ones here were just genetically, it's just, you know, it sucks, but genetically they were just likely to get it and they got it very soon. Whereas these were just genetically favored, or it just took a long time, or maybe they developed it because of lifestyle. Maybe by the time they reached that age, they became a little more lethargic, a little less exercise, and maybe that led to it. I don't know. I'm not a doctor. I do the math. But when you do studies in general out there in the world, you're going to want to look for explanations for why things are true, because presumably, whatever reason you're doing the study is to promote some kind of increase of information. And your explanation for why something is true might very well lead to a deeper understanding beyond your study, depending on what it is that you do. Just be aware of that. I know I teach the techniques, but I'm not a statistician, so I don't always go out there and actually do studies myself. That's not what I do. Here's another example. Crime in California. The histogram shows the violent crime rates for the 368 California cities with at least 10,000 residents. So there's 368 data points here. And we're measuring violent crime per 100,000 residents. Los Angeles, for example, has a violent crime rate of 719 per 100,000 residents. Which bar of the 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, which I could have gotten that 1600, but anyways, out of the 16 bars, which one is Los Angeles in based upon the data provided? Which bar is Los Angeles in?
The 7th one?
1, 2, 3, 4, 5, 6, 7. This one here?
Yeah.
Well, let's think about it. What number's right there?
That's 600.
And what number's right there?
7. Oh, so green. I don't know. Down.
Which one should it be?
So the following one after.
The following one, right? So Los Angeles is somewhere in this one. Agreed?
Yes.
Yeah.
Okay. Here are the violent crime rates for the 86 California cities with 90,000 or more residents. 100,000 residents, sorry, 10,000 residents, there were 368 cities. But now with 90,000 or more residents, we only have 86 cities. And it says Oakland has the highest crime rates. Estimate this rate. If you had to give a guess for Oakland's crime rate, what would you guess? What value would you guess? How many violent crimes per 10,000 residents?
$1,499.
So you're guessing then that in the last bar, it's all the way on the right side.
If it's the most violent, yes.
Well, I mean, it's more violent than everyone else on this list. But how many are in that bar? How many cities were in that last bar?
Two.
It certainly looks like 2, correct? So couldn't it be like 401 and 1400, sorry, 1401 and 1407? Wouldn't that make Oakland the highest?
It could, yeah.
So why guess, statistically, why guess 1499? If I had to guess and pick a specific number, I'd say, okay, well, there's 2 cities in that bar. And if those 2 cities are equally spaced in the bar, that would be more like 1467. Right? A third of the way through the bar is 1433. Another third of the way through the bar is 1467. And then the last third of the bar is all the way to the end. Does that make sense?
Yeah.
So I would, if I had to guess, I would say approximately 1467. But to be honest, we have no idea where in this bar they fall because we don't have that data. So some people would say 1450, just take the middle of the bar. For lack of any other information, take the middle of the bar. For me, we have a little bit more information, which is that there's 2 in there. And because there's 2 in there, it's more likely that one is just to the left of the center, one is just to the more right of the center. I think 1467 seems more reasonable. But I wouldn't take off if someone said 1450. Now, how does this distribution compare with the one for 10,000 plus? Here's the one for 10,000 plus again. And now here's the one for 90,000 plus. How do these distributions compare? What would you say to a question like that? How do these distributions compare?
Well, the one for 90,000 has like a lower frequency.
Well, yeah, it has a lower frequencies because there's only 86 data points, right?
Yeah.
Yeah, I mean, you're certainly going to have less data points. That's true. But I think what they're asking more is in terms of the shape, in terms of the center, in terms of the variability, in terms of the various things that we were addressing in the last couple slides. How do these 2 compare? So where would you say the center for this one is? If you had to give this one a center, a balance point, like if you built this physically and then had it kind of, balance on your finger so that it didn't tip over, where would you place your finger on this one?
Under like the 250 or 300?
Right here? Well, it certainly is the thickest and the highest here, but the long tail would kind of move the balance point a little to the right, I would think.
You mean when you were asking, like, is it skewed to the right? Is it skewed to the
Yeah.
left?
So
Okay, so it's skewed to the right.
yeah, this one's certainly skewed to the right.
Okay.
And because of that, the balance point, so someone guessed around 500. I think 500 is a pretty good guess, but even that might be a little too far right. Maybe 400. Again, it's hard to eyeball these things.
Okay, so it doesn't matter that
on the other side of the 500, you have a lot more frequency.
Well,
Like
you don't
higher-
have, you actually don't have a lot more. You mean on this side?
No, on the other side.
Oh, yeah. So think of like a teeter-totter. Remember playing on teeter-totters when you were a kid? Or seesaw, what are they called?
Yeah. Mhm.
Okay. And you're able to lift someone who can weigh a lot more than you by being further from the fulcrum. That the further from the fulcrum you are, the more lifting possibility you have. Like they can be very heavy, but if they're near the fulcrum and you're at the end, you can lift them in the air, correct?
Yeah.
So it's not just the weight, but it's how far the weight is from the fulcrum that matters. On the right side, you have this long tail. So the weight is low, but you're further out. On the left, it's very heavy, but the tail, but the distance from the fulcrum is very low. So the balance point would be, again, hard to eyeball these things, but somewhere I would think around here, I think would be reasonable. Does that seem reasonable?
Yes.
I mean, if you really wanted to try to do a better calculation, you can actually try to compute the average of these, which is, since we don't have the individual data points, the best I can use is the center of each box. So like, for example, this one, this is 50, right? In the center is 50. And how many people do I have right around 50? What's my count? How many 50s do I have?
35.
About 35 or so, give or take. That sounds maybe if this is 30.
37. maybe.
I would not think 37. I would think somewhere around 35, somewhere in that vicinity. Maybe a little less, 33. I mean, does this look like it's 30, halfway between 20 and 40? And then this is halfway between 30 and 40. So this is, I don't know. Again, it's hard to get a good exact value when you don't have the individual data points. But certainly somewhere around here, I think seems reasonable. Versus this one, which I think would be further to the right. Does it make sense that it should be further to the right? What do you think? Does it make sense?
Yeah.
I think so, because, you know, if you have 90,000 or more residents, bigger cities, I would expect a higher violent crime rates, which means amongst these guys, you have more on the more violent side. But again, that's just me. You know, I'm not a sociologist. I can just, you know, do the math. Here, there's no gaps. Every bar has at least one, if not more. Here, there are some gaps, but they both look skewed to the right. There's no question about that. Right? This one comes up, and then we have this long tail to the right side, the same one for the other one. So certainly a lot of similarities between them. Okay. Again, not a lot of math in that. It's more just conceptualizing what's going on. Not very exciting either. Stem plots, on the other hand, are a little bit more fun. Why are they more fun? Because they're a little more mathy. I kind of like stem plots. So a histogram can display an enormous number of values. Unfortunately, the exact values are unknown. Are always not shown. We don't have that information. We lose it. A stem plot, or a stem and leaf plot, is kind of like a histogram. It includes the exact values, but it tends not to be used when you have lots of values because it just takes a lot of time to make. So how do we make a stem and leaf plot? So here is the exact same data for our presumably the same 69 hamburgers that we had before. The first data point is this one, 0.3. Okay, the first one is 3 grams of saturated fat. The next one is another 0.3. Another 0.3. So there's 3 hamburgers with 3 grams of saturated fat. What is the next highest in terms of grams of saturated fat after the 3 that are only 3 grams each? After the first 3 data points.
4,
4. How many 4s do we have?
4,
4. 0, 4, 0, 4, 0, 4, 0, 4. How many 5s do we have?
5,
5. Let's skip ahead. How many 15s do we have?
1, 2, 3, 4.
Excellent. So the 15s are all 1 and then a 5 or a 5 or a 5 or a 5. So the idea of a stem and leaf plot is you have a stem, like a branch. You have the stem, which includes 1 digit. And then the second digit are the leaves. The second digit goes on the right side. And every one of these goes with its stem. So 0, 3, 0, 3. We have 20, 20, 20, 21, 23, and so on. Does that make sense for how to construct or how to interpret a stem and leaf plot?
Yes.
All right, so it says here, Dave's single cheeseburger from Wendy's has 13 grams of saturated fat. Where can I find the Wendy's hamburger? 13 grams, where is it located?
On the third one.
Third line, which one of the third line is it?
The 3.
This one right here. That's the Wendy's. Okay, of course, it's associated with the 1, as are the rest of them in the row, but that's the Wendy's. Now, you'll notice that with a stem of 0, I have 2 lines. 1, 2 lines, 2, 2 lines, 3, 2 lines. That's a choice that you make if there's lots of data and you want to split it up. But if I wanted to make a stem and leaf plot with 1 number for each stem, 0, 1, 2, that's perfectly fine as well, depending on what I'm trying to show and how hard it might be. So if I wanted to add 34 grams of saturated fat, if I wanted to add a hamburger, 34 grams, where would it be? How would I add 34 grams to my?
Would you add the 4 on the empty 3 since it's empty?
Which one, the first or the second one?
The first one?
The first one. I just add a 4 right there because you'll notice the first ones are all 0 to 4s. 0 to 4s, and then 5 to 9. Then repeat. 0 to 4, 5 to 9. 0 to 4, 5 to 9. 0 to 4, 5 to 9, and so on. Does that make sense?
Yep.
Questions on that at all? Okay, now it says this table shows the number of calories in McDonald's and Burger King burgers. Okay, so McDonald's are the top 1, 2, oh yeah, I can do better than this. McDonald's are the top half, and Burger King is the bottom, and it says make a back-to-back stem plot to compare the 2 distributions. A back-to-back stem plot. So what I will do is as follows. Back-to-back stem plots. So I'll make my stem area. And what do I have? I have 2, 3, 4, 5, 6, 7, 8, 9, and 10. And let's do McDonald's on the right side. Okay, so if I interpret this by ignoring the last digit, because the last digit is 0 for all of them, then where would I put the McDonald's hamburger? How would I put that in my stem plot? what would I do to create the McDonald's hamburger?
Put a 4 and a 9 after the 2.
A 4 and a 9 after the 2. And I would interpret this not as 24 and 29, but 240 and 290. Okay, what about the 530, the Big Mac? What would I do with that?
Put a 3 and a 2 after the 5.
And put a 3 and a 2 after the 5. And what about what else do I have here?
7, you would put 2 and 5.
7, I would put a 2 and a 5. So that is McDonald's. Now, what would I do for Burger King?
You would go back to the 2 and put a 2 and a 7.
On the other side, because this is the Burger King side.
Okay. And
Okay,
then, after the 6, you'd put a 3. After the 7, you'd put a 5. After the 8, you'd put a 5. And after the 10, you would put a 0 and a 4. Or just-
not a 0, because remember, there's only one data point here, right? If I had 2 numbers here, that would be 2 different data points.
Right.
So what's the one number that I would put here?
4.
Just a 4. Right? 104, 1040.
Okay, yeah.
Make sense? So this is my back-to-back stem and leaf plot where I can visualize Burger King and McDonald's. If you really, really, really want to have lots of calories, where should you go? Burger King and McDonald's?
Burger King.
Burger King, yeah, that's what I'm talking about.
So just a quick question. So when it asks for the back to back, we're not supposed to do like how you were talking about before, where it was like how they separate 0 to 4 and 0 to 9.
No, you could. Remember, the 0 to 4 and 5 to 9 separations when you have lots and lots of data. Here, if I separated them, there's really no need to, because I don't have lots of data. So I'll just lump them together into one.
Okay.
But if I had 50 of these and 50 of those, I might decide to separate them as well. Okay, so the separation is not because it's back to back. The separation is if you feel like it's right to separate. If you feel that it's easier or simpler, or it can convey more information if you do so.
So like if this was like on a test, would it matter what we did?
Only if I specifically specify.
Okay.
Okay. Yeah. So does that make sense?
And then the zeros, we didn't pay attention to because they all end in the zero. So we just kind of like eliminated those.
Yes. So then you have to interpret the scatter plot of the stem plot. So when you see 2, 4, you have to recognize that in this example, it doesn't mean 24. It means 240.
Gotcha.
Okay. And quite often when you make these things, you'll have to, especially if you're doing it in some kind of study or paper, you'd certainly want to specify in your work, the interpretations. Does that make sense?
Yes, it does. Thank you.
Okay. So that takes us to the end of chapter 10. Very exciting stuff. Are there any questions on chapter 10, displaying quantitative data? Now's the time to ask.
Can you actually do another one combining 2 of them, like how you just did?
Yeah.
Because
Let's
if you
do it.
ask another one in the test, I don't want to.
Well, it won't be on the test. I mean, not this test, at least.
No, I know, but I don't want to have a hard time.
Okay. Well, let's take a look. Let's take a look. Make back-to-back stem plot of the treadmill data. So where's the treadmill data? Okay, so here's the treadmill data. All right, so without necessarily going through the entire thing, we can at least start it. Okay, so the treadmill data. First, do you think I'm going to want to lump them together into a single row for each number, or am I going to want to separate them?
Separate them?
Well, I could, certainly. There's not really a lot of non-folding treadmills, but there's certainly more of these, and there's lots of 7s and lots of 6s. So, okay, let's separate them. So what's the smallest number? I have a 50 here. So I'll have to start with 5 and a second 5. And of course, once I start, I don't skip anything. So 2 6s, 2 7s, 2 8s, 2 9s. And I think that covers everything, correct? Because now, oh, I don't even need the 9s. There's not even any 9s in my data. And we'll do the folding on this side and the non-folding on this side. Okay, so let's do the non-folding first. What's the smallest number I should put in my data, in my stem plot? For the non-folding, what's the smallest number I should put in my stem plot?
Zero, would it be 0 since there's no, or would it be 1 since it's a 65?
Well, why would 65, first of all, be a 1?
Be 81.
60?
So the one on the 8.
So 60 is the smallest number, correct? Going smallest to highest. So 60 is the smallest number. So what would I put in my stem plot on the non-folding side?
0
0. And where would I put it?
after the 6 on the non-folding side.
Which 6? There's 2 of them.
The first one.
Okay. The next lowest is 65. So what would I do there?
On the second 6 on the
What?
side,
Put what on the second 6?
5.
Okay, 5. And then the next one, 69. How would I represent that?
You put a 9 on the second 6.
9 in the second 6. 78.
An 8 on the second 7.
Okay, what's next?
Another 8 on the second 7.
Okay, what's next?
1 on the first 8.
Next,
The 2 on the first 8.
next,
The 3 on the first 8.
next,
A 4 on the first 8.
next.
And then a 5 on the second 8.
Okay, so that takes care of the non-folding side. Now let's go to the folding side. What's the smallest number?
0
Okay, where would I put it?
on the 5, first 5.
Okay, 5 0. Next.
Then you go to the 6 and you put a 1 on the first one. On the
Okay.
first 6, sorry. Put another 1. Put a 3. Put a 4. And then on the second 6, put a 5, a 5, a 6, a 9. And then a 0 on the first 7, 2 zeros. Then 3 1s, then 1 2, then 3 3s, and then 1 4, and then 5 on the second 7, 2 6s, 1 9, and then 1 on the 8, first 8.
That's it. Awesome. Amazing. Knocked that one out of the park. Any questions on this?
No, perfect. Thank you.
All right. Okay, so that takes us to the end of chapter 10. And we move on now to chapter 11. Measures of position. Okay, measures of position. I'd stop now, but we have like 25 minutes more of class, and that's a lot of time, and we should really use it wisely. So the graph on the next page was made using Social Security Administration records. So this is the graph. Let's take a look at it. It says the median ages for females with the 25 most common names. Emily, Ashley, Sarah, Jessica, Anna, Jennifer, Elizabeth, Laura, Lisa, Karen, Susan, Donna, Sandra, Patricia, Nancy, Linda, Mary, Margaret, Carol, Barbara, Ruth, Francis, Helen, Betty, and Dorothy. Do we have any of those in here? I think we have an Emily. I'm pretty sure we have an Emily. I think we have an Ashley too. Yes? Don't we have an Emily and an Ashley? Or at least an Emily?
Yes, we do have an Emily.
What else do we have? Anyone else have their name here? Apparently we have a very uncommon class then. Says, what else? Yeah, I think Emily's the only one. All right, well, I'll complain to the name calling people that we should have more more disparity in names, but when you look at this, are there any names on this list that are kind of going out of style? That you don't really see kids being named that anymore?
Francis.
Francis, yeah. Francis is a big one. I don't really know many Francises. I mean, I know Betty White and Betty and Veronica, but other than that, I really don't know many Bettys.
Ruth.
Ruth. Yeah, Ruth is up there. So does it seem reasonable that the median age for a Francis or a Ruth or a Dorothy should be like in the 60s and 70s?
Yeah.
Like you really don't have many young people. You have some, but not that many, right?
Yeah.
Now, Emily, Ashley, Jessica, these are more hip names. I don't know if that's the word you want to use, but
More hip.
I don't know. I mean, like, you know, more, what's the word I'm looking for? More modern, the more,
Yeah, more modern.
Consistent or
I don't know. I mean, like, you know, I don't even know what to say here.
I mean,
Yeah,
I know
think
a
the
lot of
word
Sarahs
modern
in your
was
life.
good.
Huh?
I think the word modern was good.
Yeah, it's certainly more common. Certainly more common. But yeah, it's just, you know, names change. I mean, I know that when Game of Thrones came out a couple years ago, I don't know if any of you read the books or at least watch the TV show, but there's a few of the characters, their names became very popular names, not very popular, but somewhat popular names out there in the world. You know, people started naming their kids names from literature, you know, from books. Oh, I like that name. You know, and just started naming their kids. So names, they go through phases.
My dog is named Khaleesi. So
Your dog is named Khaleesi. There you go. How original is that, huh? Yes. So exactly. All right. So the graph on the next page was made using Social Security Administration records. Okay. The median for a given name is the age at which half of the females are younger and half are older. So let's look at the Emilys. The median age for Emilys is what, 17? Right, and here's 15, this first dotted line, here's 25, the second dotted line, the 17 seem reasonable?
Yeah.
That means half of the Emilys in America, based upon the Social Security Administration records, are under 17 years old, and the other half are over 17 years old, which seems to indicate that there's lots and lots and lots of young people named Emily, right? If half of them are 17 and younger, okay? Now, the end points of the boxes are the 25th and 75th percentiles. Now, this is a very important concept. Essentially, here's what happens. You have the median, which is the midpoint, 50% less, 50% more. This left edge of the box, called the first quartile or the 25th percentile, separates the bottom 25% from the next 25%. So 25% of Emilys are here, 25% of Emilys are here, 25% of Emilys are here, and then 25% of Emilys are over here. Now, I don't know what the maximum is. They didn't give me that information, but 25% of Emilys are 26 or more. 25% are between 17 and 26. 25% are between, I don't know, 11 and 17. And then 25% are less than 11. Does that make sense, this idea of what the 25th percentile, the median, and the 75th percentile do in terms of separating the data points? You're essentially separating it into 4 equal pieces: the bottom 25%, the next 25%, the next 25%, and the top 25%. So use the 75th percentile in a sentence about the Donnas. You don't see many Donnas these days. So somebody describe in words, or say a sentence in words that uses the word Donna and the 75th percentile and makes sense in the context of what we're doing right here. Anybody?
Wait, so Donna is in the 75th percentile?
Well, here's Donna, correct?
Yes.
Like everyone else, she has a median, a 25th, and a 75th percentile. All of them have a median, a 25th, and a 75th. I want to know a sentence about the 75th percentile for the Donnas. Or somehow use that information in a sentence.
According to the Social Security Administration, the name Donna, I don't know, the name Donna lies in the 75th percentile of most common names.
No, but again, you're not quite getting it. The 75th percentile is a number. In the case of Emily, the 75th percentile was 26.
Yeah.
That number is the 75th percentile. So what is the 75th percentile for Donna?
65.
65. So what does that mean? That the 75th percentiles for Donna is 65.
Would it be younger?
Would what be younger?
Younger, like the 75%, like females that are Donna are younger than 65.
Yes. 75% of Donnas are under 65 years old. That is what it means that the 75th percentile is 65. 75% of Donnas in this world. If I meet a Donna at random, there's a 75% chance that you'll be younger than 65 and a 25% chance that you'll be older than 65. Does that make sense? Yes, no?
Yeah.
Makes sense? Everyone?
Yes.
Everyone else?
Yeah.
We get, from more than 4 people, some confirmation. Okay, a thumbs up.
Yes.
Which name has the biggest box?
Anna.
Anna. What does this tell you about that name?
People between 15 and over 55 are named Anna.
People all over the place are named Anna. There's young people named Anna. There's old people named Anna. There's lots of Annas.
It's the most common name
Well, what do you mean it's the most common name?
according to the chart.
That doesn't say that, actually. It doesn't say anything. Well, it just says that these are the 25 most common names. Doesn't actually tell us which ones are more common than others. Although I imagine it's probably listed from most common to least common. So I think Emily is the most common. Okay, as of January 1st, 2014, huh?
Is it that there's more Annas alive?
No, doesn't actually say that.
Does it have like the biggest range? Like it has like the biggest, like, I don't know, the range of how old people are that have that name?
So yes, it's certainly connected to that. Someone texted, it's the most continuous common name. Love it. It has been a common name for a long time because 25% of Annas are under 14. So there's lots of young Annas. 25% of Annas are over 63 or 62. So lots of old Annas. 25% are between 14 and 31 or so. So there's lots of Annas in that range. And 25% are between 31 and 62. So there's lots of Annas at every age group for the most part. Anna has been common for a long time. Does that make sense?
Yes.
Which names have not been common for a long time? Well, there's lots of them, so maybe it's a tough question to answer. But maybe I do it this way, which name was common for the shortest amount of time? Or seems to be common for the shortest amount of time?
Jessica?
It looks like it. Jessica was really common for a short time. I mean, what age is this? It's about 20 to 30. So there was a 10-year gap. There was 10 years where there were lots and lots and lots of 50% of all Jessicas are in this 10-year range. And then 25% are all more and 25% are less. So there's still Jessicas being named and there's still older Jessicas. But for this 10-year gap, fully 50% of Jessicas were born in a 10-year gap or 10-year interval, which means it was really, really common for a short time. Was there like a very famous Jessica? Let's see, this is January 2014. So 20 to 30 years before that, 1984 to 1994. 1984 to 94. Was there like a really famous Jessica, like a singer or an actress or something that people would have named their kid after in that 84 to 30? You guys are all young. You guys don't know what the 80s are like anyways. All right, anyone here old? Well, don't answer that question. It's a bad question. Anyone here born in the 80s or 90s? Maybe the 90s. But not the 80s, right? You were born in the 90s?
Yeah.
But not the 80s, right?
No.
No. So I was born in the 70s. Let's not go there, but we just did. And I don't really recall anything happening in 84 to 94. But sometimes there's a boom of some kind and just some names are just popular for some reason. I don't know how it works. Anyways, does this make sense so far?
I have just like a clarifying question, Professor.
Yeah.
So the graph shows only starting from like the 25th percentile to the 75th percentile.
Correct.
But like 0 to 25 they're still there. They're just not on the graph.
Yes, they're still there. I mean, listen, if you go to the hospital right now, if you go to every hospital in the world, I'm sure you're going to find babies that were just born whose names are Emily or Ashley or Sarah or Jessica and so on. Right? So these names go all the way to immediate. It's just there's not as many. Okay, we're only coloring in the middle 50%, but there's still 25% younger and 25% older.
Okay.
And Regina, I saw Jessica Jones. I was never really a comic book fan, so I don't know who that is. But did that come out like right around that time, 84, 94? I don't know.
I'm not sure either. It's just there's like a lot of actresses with Jessica's name.
Jessica
Simpson, Jessica.
Simpson, that's right, Jessica. I remember that one. And
There Jessica Parker.
Oh, well, that's Sarah, really. But then again, Sarah's on the list too, right? Right next to it. Oh my God, Sarah Jessica.
Oh my God.
Maybe that means something. I don't know.
Professor, I have a question.
Yes.
So the estimate of the 75th percentile for Emily would be 26, but the 25th percentile would be what, 15?
Oh, not 15, because the gap from here to here, this is a 10-year. No, this is 15 right here. Right?
Yeah.
I think because it's 75, 65, 55, 45, 35, 25, 15. So I would say closer to 10.
10, okay.
Yeah. Again, it's just a representation, so it's not 100% exact, but this seems to be about 10. Right? So I don't know. Anyone either have a kid with any of these names or is planning on having a kid with any of these names one day?
No.
No Dorothys or Francis's?
No.
No?
No Dorothy's. And then Dorothy could have been because of the Wizard of Oz.
Well, yes, but that would have been
the old.
yeah, 100%. Could very well have been.
Yeah.
Betty White's, I don't know.
And then Donna because of that 70 show and things.
Oh,
Like
Donna. That was a great show.
that. Yeah.
Yeah.
See?
Of course, I think Karens are going to kind of go out of style soon.
Oh yeah, Karen. Nobody's gonna
Very
get
smart,
Karen.
like ooh, like a
Which
long
one?
time. ago.
Which one?
Karen, it's like it just did.
Yeah. Karens somehow sound like they're going to go out of style. I don't know. I just had this feeling.
But if you're Karen now, it's just you're made fun of. So
It's a bad thing. Yeah. Anyways, so now let's talk about percentiles. So we just talked about the 25th percentile is the point at which 25% is beneath. And the 75th percentile is the point at which 75% is beneath. Well, why stop at 25 and 75? I can do this for any value. So the 10th percentile is when 10% is beneath. And the 90th percentile is when 90% is beneath. You ever take a standardized test, in school, and they said something like, oh yeah, you're in the 85th percentile? You ever
Yes.
wonder what that meant? You're in the 85th percentile. It means 85% are lower than you. Okay, Essen, have fun. Or hope everything's okay. Okay.
Thank you.
You're welcome. All right. So Maria, a 6-year-old, is at the 65th percentile in height for girls her age. The 65th percentile. Explain this statement to her parents who doesn't quite understand it. How would you explain it to a parent? Hey, your kid is in the 65th percentile for height. What would you say to her?
Could it be something like Maria is taller than 65% of girls her age?
That's exactly what I would say.
Awesome.
And that's exactly what it says, right? Okay, I don't understand. Your child, Maria, is taller than 65% of all girls her age. So she is in the upper end of the spectrum, but not too far up the upper end of the spectrum. She's a little bit above average. Right? Does that make sense?
Yeah.
Yeah.
All right. So now, yeah, we can do this. Okay. So now the cumulative percentile or percentage plot shows the amount of change carried by 200 students. So there's 200 students here. On the horizontal scale is how much change they carry. So some carry nothing. Some carry 25 cents, 50 cents, 75 cents, 100, 125, 150, and so on. So according to this, approximately at least, what percentage of the 200 students that we interviewed or surveyed carry 0 cents? What percent carry 0 cents?
15.
Yeah, is that about 15? Let's take a look. I mean, that's a little high, is it? Maybe, would you say that's about 10%?
Yeah.
And that seems to be, yeah, I think 15% is a pretty good guess. You guys agree with that? 15% approximately?
Mhm.
Okay, so 15% of students, oh, I have the wrong thing. So 15% of students carry 0 cents. Now, what is the total percent that carry between 0 or even up to 25 cents? Because remember, this is a cumulative percentage plot. So it doesn't give you the exact amount for 25 cents. It gives you the total amount up until 25%. So what percent carry between or any amount up until 25 cents? Anyone, what percent?
That's already like 20%. So it'd be like 20% plus a 15. Would it be like 35%?
Well, just take a look at this number here. How high is that?
Like
Oh, okay.
55,
How much? I'm sorry.
like 55, 50.
Okay.
Okay.
Let's, even if it's not exact, let's just round it to 55%. So 55% carry up until 25 cents. So how many carry approximately 25 cents?
55.
How much?
70.
Oh.
Not 70. No, I mean, up until 25 is 55%,
Oh, I thought.
right? Up until, right? So what percent carry exactly 25?
Wouldn't it just be 55?
Well, 55 is up until 25.
You say cumulative, so it'll be 55 plus a 15.
No, not quite. Not quite. No, not 65
Oh, okay.
either.
Is it 40?
It's 40%. Because between the two of them, it has to add to 55%. And we already have 15 at the 0,
Oh, okay.
right? The total, yes, Carl, the
So
total,
instead of adding a, you subtract. I got it.
okay. So what percent would include up until 50 cents? What percent would be up until 50 cents?
Would be 60.
63.
Okay, let's say 63%. So what percent would be exactly 50 cents?
Like 23?
Not 23,
28?
not 28.
Wait, I'm sorry. How are you getting these numbers?
I'm reading them off the graph. So this right here is about there, which is about 63%, because here's 60, here's 80, so I'm guessing around 63.
Oh, wait, you would just subtract the 55, no?
Yes, so what do you get?
8.
8%. Because remember, we already have 55% by the time we reach here. It's 63% by the time we reach here. So the jump is from 55% to 63%.
Yeah, the difference of that, yeah, the cumulative. Okay.
Okay, and what will be 75 cents?
That's 80%.
Well, the total is 80%.
Oh, you're asking for the difference already.
Yeah, so what would be the amount that carries 75 cents?
17%.
17%. So now we can answer questions as follows. What percent of students carried 50 cents or less?
63%.
63%. I can read it right off the graph. Now, what percent carried $1.50 or less?
Would it be maybe 90%?
Okay, I like 90%. Someone chatted and they said 90%. Good, yeah, that's what I would guess. So 90%. Now, better question. A student at the 40th percentile carried how much? A student at the 40th percentile carried how much?
Like, I don't know if I'm wrong. Like 10 cents?
Well, I'll take a look. Here's 40 percentile, right?
Yeah.
And that will be the amount that would correspond to the 45th percentile, to the 40th percentile.
So would it be 15 or less?
It looks like about 15 cents, yeah. Does that make sense? Haha, no pun intended. And what about a student at the 50th percentile, which is the median, by the way, right? The median is the halfway point. So a student at the median, the halfway point, how much change would they carry? So,
25.
well, let's take a look. So here's 50. No, that wasn't 50. Let's try this again. 50, about there. And we go down. Yeah, it seems very close to 25 cents. Yeah, we agree?
Yeah.
About 25 cents. So these cumulative graphs can really allow us to calculate percentiles when we don't have any additional data. It's 3:16. I don't want to go over. We will stop here, and I will see you all on Thursday.
Hi, Professor.
Have a good day.
Thank you,
Thank you.
Professor.
Bye, guys.
Good one. See you Thursday.
Okay.
See you Thursday. Have a good day.
You too.
Happy World Teacher Day.
Happy what?
World Teacher Day.
Is that what today is?
Yes,
Well,
sir.
thank you. You're the only one who remembered.
You're welcome.